use a lagged y variable. So if we're going to use the previous month return as an independent variable, okay, well that's going to cause lots of potential problems, and we're going to revisit that in the next reading. Okay, and then forecasting the past, what if we use market cap, and we use it correctly, we use log of market cap, but we're trying to explain the return today. That's a terrible R. So we're trying to explain return today, and it's going to be a function. Okay, so it's monthly returns. We want to know what the return is going to be in April. Okay, and we're going to use the market cap, okay, from May 1. Okay, well, what's the problem with that? Well, the market capitalization on May 1 is going to be partially determined by the return in April, right? So if the market's up or the stock's up, then the market cap's going to be big, and if the stock's down, then the market cap's going to be small. So what we're trying to forecast here, the return for April, is embedded in this market capitalization number that we've got here, and that's just going to cause lots of problems. So we're trying to forecast the past. We can get models with high R squares, but then when we actually go try to use them, we say, well, why isn't that working the way we hoped it would? And that's because we don't have a crystal ball to use that on an ongoing basis. Measurement error may be free float, actually proxies for corporate governance. So, the more free float you have, the better the corporate governance, and so it's the corporate governance factor, not the free float, that is important. All right? Okay, a couple of, sort of wrap-up things here. What about qualitative dependent variables? So in essence, we're talking about a binary dependent variable. So we talked about binary independent variables previously. Binary dependent variables, we're trying to explain a 0-1. So it would be like a default model. So you can either default or you don't default. You're either pregnant or you're not pregnant, right? There's only two outcomes. Well, we want to use that as the dependent variable so we can understand whether or not this firm is going to default. Well, here, there's one big main point that you got to get here, and if you get that, then everything else is going to be sort of secondary, and that is, if you have a binary independent variable, that's okay, but a binary dependent variable, okay, that is the response variable, the y variable, you cannot use OLS, or ordinary least squares, which all of this reading is based on. Why? Because it's not that your inference is just going to be flawed, it's going to be wickedly flawed. Okay? So you can't use a 0-1 as the dependent variable. It's okay to use it as the independent variable. If you really want to do this, you want to create a default model, there are other models. I wouldn't worry too much about them. A logit model, okay, it's based on a logistic distribution. A probit model, okay, it's a probability-based model. And discriminant model, this actually assigns scores. They're all interesting, but there's no data or there's no information on them in the curriculum. So the main thing you need to know is that you can't use a binary or a qualitative variable as the dependent variable in an OLS regression. Okay, so focus on the basics there. Okay, and economic significance here, to kind of wrap up the reading, and then we'll go back and summarize. Okay, well, just the point here is remember that statistical significance and economic significance aren't the same thing. So we can go in and find statistical significance. Okay, so that's going to be based on how carefully we specify the model and whether or not there's any assumptions or violations, all that sort of stuff. But even if we get all that right, and we find that when there's a certain corporate event, there is a statistically definable or statistically identifiable reaction, but it's so small that you can't do anything with it, then there is no economic significance. So what you want, of course, is to identify things that are statistically significant so that you understand that they are there, and then they are also economically significant so that they mean something in the real world. Think of it as being able to trade on it and make money or something like that. Okay, and that is the end of this multiple regression reading. I think that multiple regression is the workhorse of the discipline, and I still think it's something that you really want to be on top of for the exam. So make sure that you get on top of multiple regression. That's not to say to ignore time series stuff, but this multiple regression is going to be a key variable when you look at the material that is available to make up test questions. So some things to remember here. Okay, so we started off talking about hypothesis testing and the coefficients, all that sort of stuff. We talked about individual testing and testing the entire model. Okay, we did the predicted y value. So we just plugged all of the we estimated all the coefficients and we plugged in predicted values for each of the independent variables. Remember, you use those the predicted values of the independent variables whether or not the coefficient is significant. We talked about the ANOVA table. And I think the ANOVA table is important. Okay, it's sort of a game to fill it all in. Then you need to be able to do a couple of things from it. Calculate the R-square, calculate the standard error of the estimate, be able to do the F-test from the ANOVA table, that sort of thing. So it's really a game plus 3 calculations, if you want to think of it that way. And then finally, all this regression analysis stuff. We talked about the problems. We're going to be able to define what they are, describe the effect, how do we detect them, a little bit about how we correct them. Also, I wouldn't ignore the model specification stuff that we've seen here at the end. So that's multiple regression. You're going to have to answer a lot of questions if you're not used to working on this in order to get on top of it. But in the end, I think you'll find that this is something that you can get on top of and that you can do well on the exam with this material. So I would think this is a good area of study for the exam. All right, the last of our big quant topics is time series analysis. This one I think is actually perhaps a little more intense than the other two. It is certainly more intense than the first one. There are some ins and outs, and you kind of have to work a little to understand what we mean in terms of the data we're using, those types of things. But once you get that, I think you'll see that this is a reasonable way to approach quantitative analysis of a series of variables. So anyway, so this is something that is, I guess I would say, expert spear to tread here. So be careful with this. Make sure that you don't get bogged down in the minutia before you get the big picture of what's going on. All right. So time series models. We're actually going to see two things here. The first one we're going to see is what's called trend models. Trend models are where we're going to look at a trend through time. So you're going to find that that's not particularly difficult, but nonetheless, it is something we'll spend a little bit of time on. We'll have two flavors of that, a linear trend model and a log linear trend model. And then the second is the lagged models. Now, it's the lagged models, or the AR models, that I think you will find to be the most challenging, and that's probably where we're going to spend 80% of our time as we go through this topic area. So those get a little more intense, and there's a few more ins and outs you have to get on top of. So when we say time series, what we mean is just that. A time series is a set of values for a particular variable for many periods of time. So you can have quarterly sales every year for the last 5 years, monthly CPI, daily returns over the last 6 months, whatever it happens to be, but these are time-ordered variables. The difference between what we're doing here and what we've done in the past is we only have one column of data. So if we're looking at this and we say, well, what is the data going to look like? Then if you're looking at a spreadsheet, what you're going to see is you're going to have, well, that didn't turn out very good. You're going to have, column A, okay, and over here is going to, in column A, you're going to see the data. It's going to be like, 3, and then 7, and then 12, and then -2, and then 1, or whatever it happens to be. That's all the data we have. We have one column of data. So it's not like what we saw in the regression analysis where we were taking one set of data and regressing it against another. We only have one column. In the case of time series stuff, what we're actually going to do is say, well, we don't have any other data, but what we do have, if we're looking at a spreadsheet, so this is column A, what we would see over here would be the row numbers, right? 1, 2, 3, 4, 5, and then that would, of course, keep going. Well, if I can make the 5 there. That would keep going for however long we had the time series. So in a time series, all we're going to do, or in a trend model, rather, all we're going to do is regress this data against the time index. When we get to the autoregressive models, okay, or the lagged models, we're going to take this data that we're using here, 3, 7, 12, -2, and 1, and we're going to regress it against lagged versions of itself. So on a spreadsheet, we'd take this column, highlight it, punch copy, and then we would come over one column and down one row, and we'd say, well, here's 3, and here's 7, and here's 12, and here's -2, or whatever the data happened to be. Now we've got this variable paired with a lagged version of itself, and this one with a lagged version of itself. That's what we would do with an autoregressive model. So keep in mind the data that we're using here. Let's start out with the trend models. These are, I think, a lot easier. You can see here we're taking the data we have. That's the y variable, just like we talked about when we were doing regression, and we're regressing that against the time index. So this is just a regression equation. So y is equal to b0 plus b1, a normal regression coefficient, times this time index. And there's just not much more to it than that. What we're trying to do is get some idea of what is going to be the predicted change through time, and of course the predicted change in y for each period is going to be b1. So the point is the y is fundamental data. Well, let me get rid of some of this junk. So the y is fundamental data here. So this is inflation each month for however many months, or stock returns every day, or whatever it happens to be. The time index is something that we create. So these are time-ordered series. We start with one and we number through the end of them. So we're just regressing against the time index. So looking at this, if inflation follows a trend the following inflation trend model was estimated using CPI from January 1995, that was month 1, through December 2008, that was month 168, so we had 168 observations. We took inflation each month, we regressed it against the time index. We got an intercept of 4.35 minus 0.013132 times the time index, and of course we still have our little epsilon there to remind us that this is estimated with error. So if we want to know the forecast value of inflation, that is y, for January 2009, that would be month 169 in our series, right? We started with 1 through 168. Well, the next month, what's going to happen? Well, y in 169 is simply going to be 4.35 minus 0.0132 times the value of the time index would tell us that inflation is expected to be 2.12%. I hope that is stated on an annualized rate. Now, there is one twist for this, and that is we often look at data in finance that has some sort of exponential trend. So if you look at time value of money calculations, you see that little exponent. Okay, so you've got this, the exponential factors working for you there. Well, what we're really trying to do then is we're trying to estimate an exponential function. So we look at this and we say, here's our data. We think it's going to change in some sort of exponential system. So here's the exponential. Here is the b0 plus b1 times t. You recognize that? Well, that was just the one side of the equation when we were looking at the previous model, right? Well, all we're going to do now is take the natural log of both sides. So if you were to ask me how to estimate this model, so how are we going to estimate this model with this in this exponential function? Well, that's going to be a hard thing to do. Obviously, it's a nonlinear. If you have a nonlinear model specialist, bring them in. They can look at that. Maybe they can do something with it. Okay, Andy Holmes isn't the person to help you with that. Okay, but what I could do is I could go in and take the natural log of this side and the natural log of this side. Remembering that the natural log and the exponential work inverse of one another, what we end up with is the natural log of our fundamental data is equal to this equation, which is exactly what we saw before, b0 plus b1 times t, and then the epsilon is there. So don't let log linear trend models fool you. Okay? At the end of the day, I mean, we got some mathematics for how we got there and why we got there, and I'll show you a picture of exponential versus a log linear function here in just a few minutes. But what we're doing is simply taking the log of the data, the natural log of the data, and then regressing that against the time series. All right, so it's just saying, here's the natural data, let's take the natural log, and we're going to regress that against the time series. Now, one trick to remember with this, if we estimate this equation, the natural log is equal to, natural log of y is equal to 5.01 plus 0.095 times the time index. That's the equation we've estimated. If we want to know what the estimates are at y1 and y2, okay, well then we can come in and we can say, well, let's take, we're looking for the estimate at y1 for y1, so that's going to be 5.01 plus 0.095 times 1, that's the time index for that period. That's equal to 5.105. The problem with that answer is if you saw this question on the exam and it says, what is the predicted value of y in the first period? You plug into the equation, you get 5.105. You see that as answer A on your exam. You bubble that in and you happily fail the exam. Why is that? Because that's not the predicted value of y or your estimate of y. That's the estimate of the log of y. So if you want to get it back into its true form, then you're going to have to use the exponential again, right? So we took the log to get it out of exponential. We're going to use the exponential to get it back. Those two are working as inverses of one another. So we're going to take this 5.105, put that on our calculator, hit the e to the x button, and it's going to tell us the predicted value is 164.84. So what is the estimated value of y1? It's not 5.105. It is 164.84. 84 or 0.84, so keep that in mind when you're dealing with these models. Now, just to see why we use the log linear, so what you see here, okay, in this first graph is an exponential function, right? So you see this nonlinearity, it's going up and up and up, which looks like a time value of money function, so you see that a lot in finance. The problem with that, of course, is if you estimate this as just a linear function, well, the linear function is just a straight line, so you're going to have some estimation errors that are going to be positive down here and positive up here, and they're going to be negative in the middle. Obviously, there's some problems with that, serial correlation, those types of things. So if you take the log linear model, then what you end up with is this, okay, and you see that you get a much better fit to the data. So the log linear model, if you have exponential traits in your underlying data, then the log linear model makes sense. All right? Okay, so that's our trend models. Now we're ready to move on to the, and I think I scooted forward one, too many slides there. So now we're ready to move on to the autoregressive models. So looking at the autoregressive models then, what we're going to see here is that we're going to deal with this idea of covariant stationarity. Okay? And this is going to be a big deal that we'll see in a little while. But the point of this here at the outset is that when we're dealing with the autoregressive models, the time series must be covariant stationary. Okay? So what does that mean? What that means is there has to be a constant and finite expected value, there has to be a constant and finite variance, and covariance with leading or lagged variables. And while some of that may or may not make sense, some of it gets to where it's fairly heady and it's mathematics and those types of things. But we're going to see, for instance, that this one is going to come into very direct play, constant and finite expected value. Okay, so we're going to focus on this first part. And the trouble with this is that a time series must be covariant stationary. We could also, you might in the lingo hear that this is a stationary series, because the opposite of that is a non-stationary time series. And if you have a non-stationary time series, then it's going to produce meaningless results. So not just that it's going to have flaws, it's going to be downright meaningless. All right? Okay, so the autoregressive model. So here's the notion. What we're going to do is we're going to take the data and regress it against lagged versions of itself. So once again, imagine that you have a column of data, okay, whatever that is. That can be returns, it could be sunspots, or whatever it happens to be. We're going to have this one column of data. Well, what we can do is copy that, move over one column and down one cell, and then we're going to have the observations paired with themselves lagged one period. Well, in that lagged version, we could copy that, move over and down one cell, and then we would have the data against two lags. That is, the data at time x regressed against the data at time x t minus 1 and x t minus 2, and we could keep doing that for as long as we want. And before the presentation here is over, we're going to see a model where we're looking at something with a 12-period lag. So that is, we're going to lag this data out 12 periods. So we can create, so we start with one column of fundamental data, and we can create as many lagged versions of that as we want to. What we're trying to do is say, is there data, is there information in the way this data changes? We're going to pick that up by regressing the data against lagged versions of itself. And of course, there's no longer a distinction between the dependent and the independent variables here. It's just the data and the lagged data that's going to be used in our models. So here's the point. If we look at this and we're going to regress an AR1 model, that means we're going to take the data, the natural data, and we're going to regress it against itself lagged one period. So once again, we have a column, we're going to copy it, move over, down one cell. So yes, we're going to lose an observation, but we're going to be regressing against the data lagged one period. All right? So when we do that, we come out with this model. It says the data, this period is going to equal to 0.07, that's our intercept, plus 0.8785 times whatever the data was last period. And then, of course, this little thing on the end is reminding us that there's error here. So the question is, if x0 is 0.5150, so that's x0, what's the forecast for time 1 and time 2? Okay, well, the point here is that we have to use a tool called one-step-ahead forecasting. Okay, so what we're going to do essentially is say, well, if we want to know what's going on at x1, so if we're going to predict what's going on here at x1, let me get rid of some of this chicken scratch. So we go back up to the original model and we say, what's going on at x1? Well, what's one period before x1? It's x0. Okay, so we're going to plug in, and we're going to plug in x0. We're going to find the predicted value for x1, just like we found predicted values in the first two readings in the quant method stuff, and we get 0.5272. Well, then, if we want to know what the predicted value is at x2, okay, well, we're going to have to take the predicted value from time 1 and plug it in as the time 1 variable, which is the lag for the 1 period lag for time 2. And that's going to give us this 0.5380. In other words, the point here is, if we wanted to predict what the value was going to be at time 180, then we were going to have to go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and we're going to have to go out from 178 to 179. Then we'll plug that in and find the value for 180. So one step ahead forecasting is the way that we use these AR1 models. Now, one more comment here. This AR1, the 1 here is called the order of the model, but from here we could go to an AR2 model or an AR3 model. The question is, how do we want to do that? All right? Well, there's a big point here, and that is, if serial correlation exists in the error terms, then the model is incomplete. Now, thinking back to what we learned in previous material, serial correlation is where the error terms are correlated. Remember, the assumption of the regression model is that there's no correlation in the error terms. We talked about serial correlation. We did the Durbin-Watson, all that sort of stuff. Okay, well, what we're finding here is a little different approach. So we had to structure our model in multiple regression. Now what we're seeing is that the creation of a model in the autoregressive realm is really an iterative process, and we let the data itself help us build the model. So what we're going to do is we're going to run an AR1 model, and then we're going to investigate as to whether or not there's serial correlation. The existence of serial correlation doesn't tell us the model is wrong. What it tells us is the model is incomplete. That is, if there's correlation in the residuals, there's more information there that we could pull into our model. So that's still information. What we're going to do is use that. The way we're going to do it is we're going to test for serial correlation. If there is serial correlation, we're going to add some more lags. We're going to add those lags. We're going to go back. We'll test for serial correlation again. If there is serial correlation, we're going to add more lags. That is to say, increase the order, and we're going to keep doing that, okay, until we have a model where there is no serial correlation in the error terms. So does the serial correlation exist? Okay, an important point here. Now, wouldn't it be nice, we spent all that time studying the Durbin-Watson exam, or the Durbin-Watson test, excuse me. Wouldn't it be nice if we could just use the Durbin-Watson stuff that we learned in other areas? Okay, the Durbin-Watson does not apply to time series stuff. That only applies in the multiple regression realm that we're working before. So here we have to use t-tests on the lagged residuals in order to find out whether there is still serial correlation. Let's summarize. Okay, so here's the point. There's this iterative process that we're going to use to develop our AR models. So first of all, we're going to run the model, and then we're going to test for serial correlation using t-tests. If serial correlation exists, we're going to increase the order of the model, and then we're going to continue increasing that until we test and we see that there is no serial correlation. All right? So how would we go about doing this? So in this case, we're going to run our AR1 model, okay, and then we're going to test the lagged residual. So remember, every observation has a residual. Think of this as running a regression. Okay, we end up with a regression line. Okay, the actual data is not going to fall in the line, so there's going to be an error term. Well, what we're doing here is we're looking at these error terms. So we're going to have a column of data. We're going to ask our computer, what is the error for each observation? Okay, we're going to take that. We're going to copy it. We're going to move over one column and down one cell. That'll be the first lag, the second lag, the third lag. Here, we're going to test autocorrelations with 4 lags, all right? So these are our autocorrelation coefficients. This is the standard error, which is a little different than what we've seen previously. It's just 1 over the square root of n. Okay, we're really not interested in this. Okay, we're really not interested in the standard error. What we're interested in is the t-stat. Okay, so when you look at this, okay, what is it that, does anything jump out at you when you look at those t-stats? Okay, so, well, what jumps out at me, okay, is the fact that this one t-stat is almost 2.4. What's that telling me? There is some significant correlation in this, some significant autocorrelation here. So this means what? Well, if there is going to be, assuming the critical t-value is 2, this means that the model is incorrectly, I might prefer to use the word incompletely, specified. So since we developed this with an AR1 model, and then we took the lags and we tested them, now we're going to move to an AR2 model. That is, we're going to add one more lag to our original model. When we do that, we're going to go back, we're going to get the error terms again, we're going to take the error terms, lag them once, calculate autocorrelation. Take the error terms, lag them twice, okay, calculate the autocorrelation again, and then 3 times and 4 times. Why 4 times? Well, that's part of the art of this. That's where we got tired. Okay, there's nothing to tell us exactly how many of these we should check. But nonetheless, when we do that, what stands out now as the t-stats on the autocorrelations? Well, notice that they are all insignificant. That is, the autocorrelations are no longer significant, which tells us we are to a plateau in our modeling. So this was what I would call the first big finding that we have as we go through this reading on autoregressive models. That is, we understand the order, we understand what it is we're doing, we're regressing the data against the data lagged one period. Okay, how do we build the model? We build the model by starting with an AR1, testing for autocorrelation, going back and adding lags until all of these autocorrelations are insignificant. So the t-test, the null hypothesis here, is that the autocorrelation is, there is no autocorrelation, and what we see here is we can't reject the null, so when we have no autocorrelation, the model is at a plateau. Now, we're not really done. There's some other things we have to learn, but this is the first big step in an AR1 or in an autoregressive model. So here we went from an AR1 to an AR2, and we were done. All right. Now, what about the idea of mean reversion? So the notion here is that these models are mean reverting. Okay, meaning that they are going to come back to some particular level. So if they are above their mean reversion level, if the observation at time X is above, then the next one's going to be below. If it's below the mean reversion level, the models are going to be pulling them back up. So the value of the dependent variable tends to fall when it's above its mean, and it tends to rise when it's below its mean. That is, its mean reversion. For an AR1 model, this little formula will specify our mean reversion level. Okay, the intercept B0 over 1 minus B1. Okay, this doesn't seem like much as it sits here. Okay, but this is going to lead us to an important conclusion in just a little while. Right? So this will be important when we start talking about the random walk models. As a quick example here, if this was the model we had, this was our AR1 model, here's our intercept, here's our coefficient. So we take the intercept divided by 1 minus the coefficient, and we end up with this, 0.6156. What's that telling us? Okay, what that's telling us is that if x0 is below 0.6156, then the forecast value for x1 will increase towards this mean reversion level. So the forecast values are always reverting back to this level, 0.6156. All right? Okay, now about forecasting accuracy. So if we're thinking forecasting accuracy here, we want to know how well the model fits the data. Well, we looked at that in a couple of ways in the regression analysis stuff, and one of the things we looked at for our goodness of fit measures was an SEE, standard error of the estimate. Remember, we just took the square root of MSE when we calculated that. Not that we're doing that here, but keep that in mind as a quick refresher. All right, so here, forecasting accuracy is measured by the root mean square error. So the root mean square error is the square root of the average, or the mean, squared error. And the point here is, where I don't think that we ought to think of ourselves as calculating the root mean square error, but what we want, if we're comparing two models, is we want the one with the lowest RMSE. So if you're comparing an AR1 versus an AR2 model, okay, you can calculate the root mean square error, and whichever one of those has the smaller RMSE is going to be the one that has the more accurate forecasting capabilities. Let's talk about coefficient instability here. The point is that estimated regression coefficients change from one time period or regime to another. So if we think of the internet bubble in 97 or 98 through 2000 or 2001, whenever it popped, well, things that were happening before the bubble burst and things that happened after the bubble burst looked different. There were different regimes there. So what we have here when we talk about coefficient instability is a problem that creates a trade-off. That is, generally, when we think of statistical significance, we can enhance statistical significance by having more data. You have more data in a time series environment, that means you want a long time series. The problem with that is if you have a really long time series, then you may have multiple regimes in there, and that's going to mess up your inference. So it's really, you're faced with a choice between the statistical reliability of a long time series and the innate stability of that is the underlying fundamental characteristics or the stability of a short time series. So you have to ask yourself when you're looking at the time period, has the economic process or environment changed during that time? And if so, you're going to want to break your sample up into multiple parts. All right, let's talk about random walks. And this is, I think, a big deal. So this is something that you may want to pay attention to. Well, I'm sure you want to pay attention to this. Anyway, so you may have read the book by Malkiel, A Random Walk Down Wall Street. In a random walk, this is the mathematical model for a random walk. What it says is that the value of x today is equal to the value of x yesterday plus some perturbation term, okay, which is, of course, going to be distributed the way we've talked about. It's independently distributed, it has an expected value of 0, all that sort of stuff. In other words, we don't have any idea. We know it's going to move tomorrow, but we don't have any information on whether the next move is going to be up or down. Now, we could have a random walk with positive drift. This is what the way Malkiel actually describes the market. So the value today is equal to the value yesterday plus some positive constant. So, if you looked at the market over time, what you would see is that over time it's going to go up, but you don't ever know if the next move is going to be up or down, right? Something like that. So that's a random walk with positive drift. Anyway, the point here, and we really don't have to worry about whether we're dealing with positive drift or not. Don't worry too much about that. But looking at this model, xt is equal to xt minus 1 plus the perturbation term. Well, we could write that mathematically. It would be exactly the same to say xt is equal to 0. So we don't have any positive drift here. Plus 1 times xt minus 1. In other words, what's implicit in this first model is that the beta coefficient is equal to 1. So beta 1 is equal to 1. That is, by definition, a random walk. So if we're looking in the AR, think of this as an AR1 process. If beta 1 comes out to be 1, then we are talking about a random walk. Now, you might ask yourself, why does that matter? Well, now we have to hearken back to our little formula for the mean reverting level, and if we plug in, what we get is beta 0, doesn't really matter what that is, over 1 minus beta 1. Well, if beta 1 is equal to 1, then we get 0 in the denominator. What does that mean? Okay, well, what that basically means is without a mean reverting level, okay, we don't have a constant and finite expected value, the time series is non-stationary, which we've already said is a big problem. So a random walk is a non-stationary process, which means the results out of that regression, or out of that estimated equation, are going to be meaningless. Well, if we run into a random walk process, can we fix it? Well, if that was the question on your mind, that's a very good question. Can we fix this random walk? Okay, well, as a matter of fact, we probably can fix a random walk with something called first differences. So what we're going to do is we're going to take our fundamental data, and it's going to be something like 2, and it's going to be 6, and I'm going to call it 1 and 5. So that's our fundamental data. Well, what we could do is we could take that data and move over and down one column. So we're going to have 2 and 6 and 1. That's not a very good 6 there. And 5, although, of course, those are going to fall out of this. So we're just looking at these 3. Now, so here's our fundamental data. So this is going to be x. This is going to be x at t minus 1, right? Well, what we're going to do now is we're going to create a new variable. Okay, we're going to create y sub t, okay, and that's going to be the first differences. So we're going to take 6 minus 2, that's going to be equal to 4, and 1 minus 6, that's going to be minus 5, okay, and then we're going to take 5 minus 1, that's going to be 4, and then we're going to start the whole process over pretending like that is our fundamental data. So that's called the first differenced data, and we're going to take that, we're going to copy it, we're going to move over and down one column, and then we're going to start with our AR1 model. When we run our AR1 model, we're going to check for autocorrelation. there is serial correlation, then we're going to go to an AR2 model and so forth. All right? So first differencing is the cure for this notion of a random walk. So the point here is a random walk is the same thing as a unit root. So, and that's just fancy economic talk. All that says is that when a variable takes on a value of 1 in economics, we say that takes on a value of unity, right? So, think of the Zen. It comes to 1. We're all coming together, so unity. So if the value is 1, then that is a unit root, is where that lingo comes from. So a random walk and a unit root are the same thing, at least for our purposes. Okay? That means the series is non-stationary, but we can fix that with this idea of first differencing. Okay? So I think this is another sort of plateau for us here. Hey, that is, we started talking about how to use the data to create the order of the AR1 model. Okay, now we've talked about a few other things, forecasting and some stuff like that. We talked about mean reversion levels. Here, when we talk about first differencing and random walks, I think this is a big deal. So you're going to want to know what's going on here, but it's nicely summarized in this little red box down here. All right, so some more stuff on roots. Here's the point. The root, that is the coefficients in a regression model, in a AR model, have to be less than 1. If they're equal to 1, that's a unit root. That's a random walk. We just said that. If they're greater than 1, that's called an explosive root. We still don't have a finite and constant variance, so it's going to be a non-stationary process also. There's nothing we can do with that. There's nothing we can do with that inside the curriculum anyway. First differencing usually cures a unit root problem. It won't necessarily cure an explosive root. So this is common when a variable consistently increases or decreases over time. So if you want to look at commodity prices over a long time, if you want to look at the stock market in the 90s, it was going up. We might end up with explosive roots there, and that's going to be something to deal with that is going to be beyond the scope of the curriculum. To show you what happens with first differences, this could be, you see that this trend is up through time. Okay, well, there's not going to be any mean reversion level there, but when we take the same data and we do our first differences, now we have a mean reverting process. There's something we can work with. All right? Okay, now moving on to seasonality. Okay, so seasonality is the next big topic. So what we're going to do here is we're going to talk a little bit about seasonality, and then we're going to launch into an example. Okay? And if you can follow the example here in seasonality, I think that whoever made this example, and once again, this wasn't me. I did create a number of the slides that you look at in the video series, levels 1 and 2, but I didn't create this slide series on time series. But this is a great example. So if you can get this down, you see what we're doing with it. We're going to be talking about the autocorrelation. We're going to be talking about seasonal lags. And then once we've estimated the model, we're going to finish off by estimating a predicted value. Well, if you get this down, I think that you're getting some traction for what you'll need on the exam. All right, so anyway, seasonality. The point here is that the data in the time series shows seasonal patterns. All right, monthly earnings figures for a retailer, that sort of stuff. Okay, think of this as looking at quarterly earnings for a toy store, okay, or monthly earnings for a toy store, if you want to think of it that way. So what we're going to see is that if we run an AR1 model, it may be that sales in November are related to sales in October. That's what we'd be looking at with an AR1 model using monthly data for earnings of this toy store. So earnings in November are linked to earnings in October. Well, there may be some information there. But if you're thinking toy store, then you're probably thinking, well, there's going to be a big seasonal component because toy stores do a lot of their business in the last quarter of the year, at least in many parts in the world where they're celebrating, Christian parts of the world where they're celebrating Christmas. So anyway, looking at that, what does that say? Well, if you want to know something about the earnings in November, you might be able to inform earnings in November by looking at earnings in October. But you may be able to get a lot more information if you take earnings in November this year and look at earnings in November last year. So that would be the seasonal lag. So you can take an AR1 model, just look back 1 month, and what we're going to finally do is add a seasonal component where we're going to be looking back 12 months. So we're going to start with an AR1 model, okay, so we're applying this to monthly earnings, and then we're going to ask ourselves, is our job done after we estimate this AR1 model? And what we'll see is, no, we're not. We're going to try to bring in the seasonal component and increase our forecasting accuracy in the process. All right, So we've got this monthly earnings data. We go in, we've got 70 months of this data going on. So we're going to look at that and say, well, let's take the data, let's move over and down one column. So we're looking at an AR1 model where we're looking at the data lagged one period. Here's the regression output up here. Really, we're not going to be using that for this example. Okay, what we're looking at down here, here's the ANOVA up here. What we're looking at is the regression data at the bottom. The intercept is minus 0.0029. The lag is minus 0.6334. We see our standard errors, t-stats, all that sort of stuff. Look, our lag is very significant. We like that. That means there is some predictive value in the model. Okay. Also notice that our beta coefficients are less than 1. So we like that. That means we don't have a unit root or we don't have an explosive root. So far this is looking pretty good. Now what we're going to do is we're going to ask the computer program to give us the residuals. And then we're going to take those residuals and we're going to check for autocorrelation with the residuals lagged once, the residuals lagged twice, 3 times, 4 times, all the way out to 12 lags. And what we're going to get is this. So here's our autocorrelations. Okay, here are our standard errors, which I don't, again, think we need to worry about too much. But then we see the t-statistics. Well, look at this. Minus 2.4, minus 2.4. Those both look like they have some significance, right? So given that we've got a fairly large N, my bet is that those autocorrelations are significant. Okay, down here again, 2.4, 2.5, something like that. Any of those 4 would tell me we probably want to, this model is incomplete. We need to increase the order of the model. But if you look at the lag for the 12 periods, well, then you get a t-stat of 8. So 8.32. Wow, that's a big lag, right? So what are we going to do with this? Well, there's a number of things we could do here. But what I want to do is I want to stay with my AR1 model, and I want to incorporate a seasonal lag, all right? So we're going to incorporate this lag into the AR1 model. That is, we're going to regress the data against the data lagged 1 month and the data lagged 12 months. So this part, okay, is what we previously called an AR1 model. What we're doing now is we're expanding that with a seasonal lag, and of course we still have our epsilon term there. So why didn't we saw the significant coefficient on the first lag, why didn't we go to an AR2 model before we did this? Well, there's some art involved in this, exactly what action we should take in response to the data we saw on the last page. There's some art there. What we decided to do was stick with our AR1 model and add a seasonal lag, so that's what you see here. All right, but that's not necessarily deterministic. If you wanted to go to an AR2 model and then check again and then add a seasonal lag, that wouldn't have been wrong. Now, what happens after we add this additional lag? Well, up here's the ANOVA. We're not going to use that again. Here is our regression data. Notice, of course, that all of our coefficients are less than 1, so we like that, which means that we're not going to have anything blow up on us. Now, let's take the error term from our AR1 model with the seasonal lag, look at those error terms, lag them once, twice, and up to 12 times to get our autocorrelation, and look at the t-statistics. And what happens here? Well, what you should notice now is that all the t-stats indicate that we cannot reject the null hypothesis. The null hypothesis is the one that says there is no autocorrelation. So what we're saying here is after we go from the AR1 to the AR1 with the seasonal lag, okay, then we check our autocorrelations. It looks like we have taken all the information that we can get out of this particular time series. So the model is now in some sense complete. We've checked for autocorrelations and we've dealt with the seasonality. Now, what do we do with that model? Well, of course, we don't regress models just to have fun regressing models. We can use that to make predictions, right? So if we want to predict the value for January 2009, so we want to come up with an earnings prediction for January 2009, remember our model, so it's going to be the value today is equal to the intercept, which we know, there it was from the regression output, 0.00048 stuff, okay? And then we know the coefficient on the 1 period lag. The 1 period lag, well, if we're looking at the model or the regression output, we'd see the coefficient is minus 0.1268. And then we're going to take the beta 2 coefficient, which we're given again from the regression output, which we saw a couple of slides ago, of 0.86. But now we want to plug into the model. So we want to plug in x at t minus 1 and x at t minus 12. Well, if you want to know what's going on in January of 2009, what is T minus 1? So, well, that's one period before January 2009. That's going to be December 2008, right? So we're going to plug that in, this 0.542, that's going to go in here. Okay? And what is 12 months before January 2009? That's going to be January 2008's data. So we're going to plug that in down here, and lo and behold, once we do that, okay, we end up getting our predicted value for January 2009 of 0.8723. So anyway, this is how we would implement our AR1 model with the seasonal lag, using the data, coming up with a predicted value. If you're with me to this point, okay, then you've got lots of traction for the exam. So this is a good thing if you're with me to this point. Okay, there's a few more things we can do with this AR stuff.